Okay, well, let me start by, before we get into the main topic today, which is continuation of um, Coulomb's discovery of the basic law of electrical force. I wanted to tell you a little bit about something I read in the paper a couple of days ago that I thought was interesting. Basically, it amounts to the modern version of Benjamin Franklin's kite experiment. The scientists today, though, don't use kites. But they have figured out how to capture lightning, in effect, in a clever way. Lightning's very powerful, but it's kind of stupid. Turns out it's easy to capture. And in Florida, they do studies on lightning. One of the purposes of these studies that these scientists are doing is to try and figure out how to protect power lines from lightning strikes. So they're in this area of Florida that's known for a lot of thunderstorms. And there's lightning strikes all the time. I mean, during the summer, there's thunderstorms every day. And so these guys set up, and they have these little pointy metal rockets, okay, that they shoot into the thunder clouds. And they've got them, they're like harpoons. They've got them copper wire stringing out of these rockets. And so the lightning takes the bait and hits the rocket and travels down the copper wire. And they can get the lightning to strike basically anywhere they want it to. I mean, if they want to see the effect of lightning on a certain kind of power line, they'll attach the copper wire basically to the power line, shoot one of these rockets into the thundercloud, get lightning to hit it, and travel down and zap the power line. And then they'll hook up their instruments to the power line and measure the amount of electricity in the lightning stroke and how long it lasts and the heat produced by it. Turns out they've discovered some amazing things, that lightning heats the air right in the vicinity of the lightning stroke to incredible temperatures of something like 50,000 degrees. So they've discovered all kinds of things about lightning, but it was neat to read about this, that these are studies that are going on in Florida right now, and these guys have figured out how to get the lightning to hit anywhere they want it to hit. And so they can make all these measurements. This one scientist was describing his job, and he said, well, it's a perfect job for a guy. I drive a truck through the woods and blow things up. So anyway, that's the latest version of what the investigations that Benjamin Franklin started. Okay, let's get back to Coulomb. And last time I started to tell you about the instrument that he invented in order to measure accurately really small forces. And it's called the torsion balance. And what it is, in essence, is Coulomb has a long wire that hangs down, and he's got it, say, clamped on some way on this end, and then he has a light rod at the bottom And now this is made up of some material that is insulating. I think he used some kind of paper coated with wax or something. So this is, say, just insulator. And then he has a little ball on this side made of something called pith. Okay, it's called a pith ball. Don't ask me what pith is. Okay, and then he's got a little counterweight on this side, so the whole thing balances. Okay, now he arranges to have another ball another pith ball. We're going to call this one the, say, fixed pith ball. Okay, and this one can't move. Okay, it's on. Yeah, Troy.
And the other one move?
Oh, the other one. You can always spin this rod. Okay. Now it takes a certain amount of force in order to spin the rod, right? Because the wire has to twist. And that's what we covered last time. Remember, the force required to twist this wire, that's the torsion force. I gave you this equation last time, right? That there's some constant. Well, let me just write the symbols and you tell me what they mean. I gave you that equation last time. Does anybody remember what that equation means? What's the K here, Nick?
I think what material it is.
Yeah, what material it is, right. It just depends on, for instance, if he has a silver wire here, then K will have one value. If he has a steel wire, then K will have another value. So it just depends on the material. Evan? Yeah.
You'll know these?
Yeah.
It's the diameter.
Yeah, the diameter, the thickness of the wire is the D here. So, you know, Coulomb found that the force, the torsion force varied. It was really sensitive to how thick the wire was. And then Salo is going to tell us what L is. Yeah, it's the length of the wire, right. And then this theta is the angle that you twist the wire through. Okay, so if you twisted this bar, you know, all the way around, and so the pith ball was on the opposite side, what would theta be? Troy?
180 degrees.
180 degrees. If you flipped it all the way, a complete revolution, 360. Okay, so this is Coulomb's basic setup here. And what he's going to do now, I mean, can you guess what he's going to do once he has this setup? Troy.
He's gonna like charge an object and like put it next to the pith ball.
Well, he's actually going to touch the pith balls, right? He's going to charge up an object. Say he charges up some glass rod, and he touches it to these pith balls. Now, they're both spheres, okay, the same size, and they're both going to take, you know, they'll both take the same amount of charge. I mean, they're in contact initially. Now, Coulomb doesn't know what that charge is. He doesn't have any way of measuring exactly how much electric charge that he's put on these balls. But for what he's trying to do, it turns out it doesn't matter, because he's going to charge both of them up, equally, okay? And then what's going to happen? They're going to repel, okay? That's going to force this wire to twist, because this ball that's movable now is going to jump away from the other one, okay, and twist the wire. Now, yeah, Dan.
How's the second pith ball fixed? Is it hanging from a wire, or how?
Yeah, he actually had it. I mean, he had this whole thing. I mean, I can complete the setup a little bit. He had this this whole thing in a glass cage. I mean, a glass container, in order to prevent any air currents. Okay, and then he had a hole in that that container up top here, and he could put, on some kind of rod, okay, he could lower this second pith ball right down to the level of the first one, and right next to it, and then just keep it in that position. And the other thing I could point out about this apparatus of Coulomb's is that he has this clamp up here. He's got basically a dial up here with degrees marked out on it. And so he can twist the wire and tell exactly what angle he's twisted it through. Okay?
So he doesn't twist it from in there, he twists it from...
Yeah, well, you're going to see why he needs this in just a minute. I haven't really explained the experiment yet. Troy?
So, if he charged it up enough, couldn't the pith ball go all the way around and then start being repelled the other direction?
Yeah, if you charged it up so much, then what would happen is it would want to get, it would end up going like as far away from this one as it possibly could, like 180, and then it would just want to stay in that position. So that wouldn't actually be good for Coulomb's experiment. He doesn't charge it up that much. I mean, I'll give you his exact data that he took in this one run of this experiment, and you can see exactly what he did and why the experiment worked. Okay, so let's, the first thing, so once Coulomb's got this set up, okay, he charges up his pith balls. I mean, he touches a charged object to them, and on this one run that this one experiment that he describes in his paper, when he charged the balls, the one that's movable, it swung through 36 degrees. Okay, so it was 36 degrees away from the fixed pith ball. So, Troy.
When you had the formula up there,
Yeah.
but if it was longer, didn't it make it easier to spin?
Yeah.
Like, so then why was it divided by the length?
It takes less force.
Yeah, it takes less force. Right, exactly. I mean, that's the reason why the length is in the denominator. The greater that length, the less force it takes to swing the rod through a given angle. Yes.
So it's 36 degrees away from the stationary pith ball when...
Right, when he first charges it up, okay, so I'm starting to, let's call this results of experiment. And I'm going to give you, see what Coulomb's trying to get here is how the force, the electrical force between these two pith balls, how it depends on distance. Okay, so here let's just measure the distance in terms of degrees. So the first measurement that Coulomb makes is the distance between the pith balls. We can just use the now in case anybody wonders about the difference between say here's a pith ball and here's the other pith ball, and there's a difference between their distance and the arc that is actually measured by the degrees, right? But Coulomb did correct for that, but I'm going to ignore it for now. And for the angles he worked with, which were generally 30 degrees or less, it's not a big correction anyway, so we're going to ignore that. But Coulomb knew about it, and he corrected for it. Okay, so they swing 36 degrees apart, and obviously the force, now the force is proportional to that angle, right? So we can call the force 36. Okay, it's proportional to the angle. We don't worry about. Yes.
How did they become apart? Like, which way did they? I mean, did it just?
Oh, well, it actually would depend on exactly what side this ball started out on, but whatever, it's just going to move away from this ball. So if I mean, this drawing is a little misleading. This ball, they should be the same distance away from the wire. So this ball should actually be, okay, so the, how do I describe this? If one of the pith balls is free to swing around like this, if you think of the pith balls as the heads of these two felt markers, then obviously if this is my fixed one and this is my movable one, it's going to move in that direction, right? It's the only direction it can move to get away from the fixed ball. Okay, so that's.
So wouldn't that
Daniel.
mean that it starts at 1 degree and it just moves? So would that mean it?
Well, 0 is wherever the movable ball started.
Oh, okay.
That's what we're going to call our 0.
Okay.
Because that's where the wire isn't twisted at all. Okay, Troy.
Did he make the glass container a vacuum to get the
Yeah,
humidity out of it?
I don't think he did. I mean, it would be slightly better experiment if he had, but I don't think the air, as long as the air is not moving, causes much of an error. So I doubt whether he bothered to pump out the air. Okay, so the initial distance is just, we can just say is measured by the angle, that 36, and of course the force is directly proportional to the angle. So we're going to call, in some units, we're going to call the force 36. Now, here's the interesting measurement. Now what can Coulomb do? Well, he can twist his wire, okay, to make the balls move closer together. Right? Okay? He can twist this thing and force the balls to move closer together. Now, he decides he's going to twist this thing so that the distance between the balls is half what it was originally. In other words, he's going to twist it until there's only an 18-degree separation between the balls. Okay, so here's his next distance is half his original distance. It's 18 now. Now, what's the force between the balls? Okay, well, the pith ball isn't moving, right? So obviously the electrical force has to be counterbalanced exactly by the twisting force in the wire. Now, how much is the wire twisted? That's all Coulomb needs to know. Well, turns out that he had to twist this dial 126 degrees in order to get the ball to move so that it was only 18 degrees away from the fixed ball. Okay, so he had to twist the dial 126 degrees. Now, there's also another 18 degrees of twist in the wire, just due to the fact that it's 18 degrees away from the 0 position, right? So the total twist in the wire is 126 plus 18, which is 144. Now, if you were Coulomb, what would you do next?
Twist it another half to make it 9 degrees.
It's exactly what he does. Yeah, sure. Try it again. Twist it again to cut the distance in half. Cut it down to 9 degrees.
And this is all measured in degrees, so of course 36 degrees and 144 degrees. This is all in degrees.
Right, right. Neve.
Did that charge leak off the balls?
Oh, it would if, if it was humid. So that would be, Troy is right that if you were doing this experiment, say in London or something, where the air is always wet, the charge would leak off these balls, maybe before you even got this one experiment done. But if you have fairly dry air, it doesn't leak off that fast, and it doesn't take very long to do an experiment like this. So Coulomb did manage to get pretty accurate results. Okay, now, so he measures how much he has to twist his dial this time to get it to go the distance to half again, to go down to 9 degrees. It turns out he had to twist it through 567 degrees.
Plus 9.
And, of course, it's twisted by that additional 9 degrees away from the 0 position. So, 576. Okay. Now, what do you make of those numbers? What can you conclude from those numbers? Well, that's the first thing you notice is obviously as the distance is cut in half, the force between the balls goes up by more than a factor of 2, right? Now, when he first cuts it in half here, how much does the force go up? Neve? Are there 12 36s in 144? 4. Right. So we've got, he cuts the distance in half, force goes up by a factor of 4. Okay, he cuts the distance in a fourth what it was originally. And you can work out that if you divide 36 into 576, you get 16. You should. So, Troy.
If you twisted it to 4.5 degrees, would it be, wait, never, I don't know.
Yeah, you can figure it out. If you cut it in half again, I mean, Coulomb didn't do this. These were the numbers, almost equivalent to the numbers that he presents in his paper. I've rounded it a little bit. But if you cut to 4.5 degrees here, this number that you should get would be 4 times 576, right?
36 times.
Every time you cut the distance in half, the force required to push those balls together that are repelling is 4 times as much. Nick. Oh, to make them touch. Well, you can't. Strictly speaking, you couldn't get 2 charges to, occupy the same spot. I mean, if you really got them completely together, I mean, not a millimeter apart, or if you really tried to bring them right on top of one another, it would take an impossibly large force. Troy.
Is it just a coincidence that all those numbers are perfect squares?
Well, no, it's not coincidence. It's the fact that I ignored Coulomb's measurement errors and rounded off the numbers to the correct values. So that's how I got these perfect numbers. Coulomb didn't actually present perfect numbers, but they were pretty close. So I just decided to make it easy. Troy.
Well, 36 was 6, and then it's 12 and 24. Is it just like it's like,
Well, these were his exact numbers. He did 36, and then he reduced it to 18 and then 9. But he didn't get for his measurement numbers on how much he had to twist his dial. He didn't get exactly these numbers that I gave you that come out perfect, but he was very close. This was a great experiment. And so you can see what's happening here. For the every time the distance, we can look at it a little differently than the way I have been saying it. Every time the distance doubles, the force goes down by a factor of 4. Okay, so what does that tell you about how the force depends on distance? If we're going to write an equation now for how the force depends on distance, obviously distance has to be in the denominator, right? Because if the distance increases, the force between the balls obviously goes down. Okay, so if we call the distance between the 2 pith balls r, is this right? Is force proportional to 1 over r? What would happen if this equation were true? What would happen if r were doubled?
the force would go down.
Force would go down, but
Force would be divided by 2.
force would be divided by 2. It would go down by a factor of 2. Well, that doesn't work. How about r squared? That works. right? Now, if you double the force goes down by a factor of 4, which is exactly what we see in Coulomb's results. Okay, so this is what Coulomb's proved. Now remember, people already suspected this, that maybe the electrical force was like gravity, that it, when we saw exactly this kind of equation for gravity last year, well, now we're seeing it again for electricity. And people had the idea that maybe electricity would turn out to be the same as gravity in this respect, because for the reason that I told you last time, that there are no electrical forces in the inside of a metal container, and people thought, well, that probably implies this kind of a force, because they'd already they knew something similar about gravity, that a hollow shell of mass didn't have any gravitational forces in it. Troy.
But how would that explain, like, if you touch an object to the side, how it wouldn't get electrified?
Oh, well, it's not obvious. It turns out that part of, I guess I can tell you this now, part of the reason that if you have some metal container, say, in a hollowed out region inside of it, and you charge this thing up, okay, that none of the charge will be on the interior surface. Okay, the reason that is, the charges are free to move in this conductor. Okay? Turns out you can prove that if, let's say you had charges on the inside wall of this container. Well, the electric charge in the metal here is always free to move. Okay, and it will continue to move as long as there's any electric forces in this metal. Well, turns out if you have charge on the inside surface here, there will be electric forces in the interior of this metal. Okay, these charges will cause electric forces. I mean, if you have, say, a positive charge out here in the middle of the metal, what will happen to it? Ben?
Negative. It would become negative.
Well, no, it won't become negative, but will there be a force on it?
It'll be repelled to the outside.
Yeah, it'll be repelled. Okay? Because it's trying to get away from these positive charges you have in the interior. So so this is, once the charges will always keep moving until they find a position where there's no forces on them anymore and they can stay stationary. Okay? Well, it turns out that charges will, even if you put charge on the inside of this metal container, the charges will move until there's no forces on them. Well, it turns out the only way that can happen is if they all pile up on the outside.
So eventually they all pile up on the
Eventually, no matter where you put the charge on this, start out putting the charge on this, this metal object, the charges will move around within that metal object, will move around until they all pile up on the outside. Because if any are left on the inside, then that will cause electrical forces inside the metal, which will move charges around. See what I mean? See how it works? So that turns out to be why you can't have charges in the interior of a conductor. Okay, now, but this is a result of huge importance. And at this point, when Coulomb figured out that the electric force obeyed this depended on distance in the exact same way that gravity does. It varied inversely with the square of the distance. Then he proposed that the law of electric force was exactly parallel to the law of gravity. Remember what we had for gravity. Force sub g for gravity was equal to a constant. Then there's the two masses that are attracting each other. Okay, so the more mass, the bigger the force. It's proportional to the masses. And then the force goes down as you increase the distance according to the square of the distance. Okay, so if you double the distance, the force goes down by a factor of 4. That's exactly what Newton showed was true for gravity. Well, for electricity, it's the exact same thing. You've got some constant which is just a number that tells you something about the strength of the electric force. Let's call it, K sub E. And then we're going to call, it's typical to use Q for electric charge. Don't ask me why. So we have the electrical force is equal to some constant K multiplied by the product of the two charges. Now this makes sense. This just means that if you put more charge, say, on these pith balls, the repulsive force between them is going to be more, right? And it's just proportional to the charges, just like gravity is proportional to the masses. Coulomb actually assumed this was true. He didn't prove it, but it is true, turns out. So, and then, again, the force goes down as the square of the distance, just like in the case of gravity. So this is the second major force law that physicists have discovered. The first was gravity, and the next is this, this electrical force. Now, and you can see how similar the equations are. So you don't even have to memorize a new equation. It's the same old equation that you knew from last year, basically. Now, Coulomb has only shown this for repulsive forces, right? Now, what about attractive forces? Now, can he make this experiment work for if he puts opposite charges on the two pith balls? Troy?
Well, he would have to twist the dial before he puts the charges on.
Right. He would have to do that. Right. He has to, in this case, he has to separate the pith balls. Obviously, if he tries to if he touches one of them with glass, charged glass, and one of them with charged amber or something, and if they're in contact, obviously, that's not going to work, right? They're just going to, right, the one charge is going to cancel out the other one, and he's going to get nothing. So he has to separate the balls and then charge them up separately. Neve, did you have a question? Oh. But do you see a problem with the experiment? Is he going to, it turns out Coulomb did try to do this. And he ran into a difficulty in carrying out the experiment. Can you see why he might have trouble? Let's say he tries to do the exact same thing that he did here. He separates the balls by twisting this dial. then he charges them up. Neve.
He can't have the two balls touch.
Yeah, exactly. That's what happened to him. As soon as he charged them up separately, the balls would tend to just fly together and touch. And it was difficult to stop that from happening. Troy.
And also, like, if he did like 180 degrees, wouldn't the balls twist and go the other way to touch? Like, go the opposite direction?
Oh, yeah, if he allowed the angle to get
Yeah.
too big. Well, I mean, on the other hand, it doesn't want to go the other way. Remember, it has to twist this wire if it goes the other way. So it's going to want to go back to untwist the wire. But it turned out to be a real problem with the balls suddenly flying together and touching and wiping out the charge. So Coulomb came up with a whole different method for doing the experiment when he had when he was measuring the attractive force between two bodies that have opposite charges. And it was it's a very clever experiment. Rather than using his torsion balance, he is going to make a new kind of pendulum, an electric pendulum. All of the pendulums that we studied last year, they all worked, right? You had a ball, say, hanging on a string, and if you set it swinging, well, why does it swing back and forth? Oh, because gravity's pulling on it, right? And it wants to always get down to this low position. Well, Coulomb had the idea of basically charging up one sphere, charging up a little object here, and setting it pivoting, and having and it would swing back and forth. This ball will swing back and forth because it's attracted to this this sphere. Let's say you charge this thing up positive and charge this one negative. And you can make a little electrical pendulum that will swing back and forth. Study that, and I'll tell you how Coulomb figured out that the attractive force had to obey that inverse square law in order to explain the results of this pendulum experiment next time. Okay, so, but for now, it's on to literature.